Factor and solve polynomial equations. Below are previously learned factoring types for quadratic expressions. So we did a lot of practice with quadratics and factoring general trinomials, so the process of reverse FOIL. Then we talked about the special case of perfect square trinomials, and that really came into play with completing the square. So trinomials that when you factor them, you get a binomial times itself, so you can write it as a binomial squared. Then there's also the special case difference of squares. So you have subtraction of two perfect squares, and it factors into their square roots, one with a plus, one with a minus. Then for the common monomial factoring, that's what we call GCF factoring. So we look for the greatest common factor for all of the terms and factor that out front prior to applying any of the other factoring strategies. Key concept: factoring polynomials. A factorable polynomial with integer coefficients is factored completely if it is written as a product of unfactorable polynomials with integer coefficients. So here are your examples: 2 times x plus 1 times x minus 4 and 5x squared times x squared minus 3 are factored completely. 3x times x squared minus 4 is not factored completely because x squared minus 4 could be factored further using difference of squares. We could factor it into x plus 2, x minus 2. So these are the factoring strategies we've known for a while and practiced a lot in the previous unit with quadratics. Let's take a look at a new strategy. So now we're going to take a look at how you factor cubes. So we have the special type of factoring for perfect squares. Now we're going to see a special type of factoring for when we have perfect cubes. So a number times itself 3 times. There's 2 different cases. With difference of squares, it had to be a difference. It had to be subtraction. But with cubes, it can be addition or subtraction. So with the sum of 2 cubes, the pattern is this. You have an a value that's being cubed. You're adding to it a b value that's being cubed. And it will factor into the product of a binomial times a trinomial. In the binomial, you have a, same sign as the original b. Then you square the a value for the first term in the trinomial. You do the opposite sign as the original. You find the product of a and b. And then this final sign is always positive, no matter if it started out as the sum of cubes or difference of cubes. And you find b squared. And so this is a pattern that you have to memorize, understand, and be able to apply. There are no other tricks to it. It's just a pattern that always works. So for example, if we had x cubed plus 27. First thing we do is identify that the a value is x. The value I'm cubing to get x cubed is x. And the b value is 3. Because 3 times 3 is 9, 9 times 3 is 27. So 3 cubed is 27. Okay, so if I'm going to factor this, it will factor into a binomial times a trinomial. So in the binomial, we put a, same sign as the original, so a plus sign. B, square the a value, do the opposite sign of the original, find the product of a and b, always positive, and then b squared. And you could check this to see that it works. We could double distribute, combine like terms, and we're going to get our original x cubed plus 27. So if we distribute the x, we get x cubed minus 3x squared plus 9x. Then if we distribute the 3, we get plus 3x squared minus 9x. Oh, I got my x on my first line. Minus 9x plus 27. So what we can see is negative 3x squared, positive 3x squared, cancel. Positive 9x, take away 9x, cancel. And so we've got x cubed plus 27. And so we can see it really does equal the original. this is the correct factorization. Okay, let's see what happens when we change it from a sum of squares to a difference. A sum of cubes to a difference of cubes. So if it's the difference of cubes, meaning subtraction, then your binomial will now have a subtraction sign, because this sign is always the same as the original. Still a and b, only now the minus sign. Still square a for the first term in the trinomial. Do the opposite sign. Find the product of ab. Then this final one is always positive, no matter what. It's positive if it's a sum of cubes, it's positive if it's the difference of cubes. And then we always end with b squared. So the only thing different between factoring the sum of cubes and the difference of cubes are the signs. These two signs are different. The final sign remains the same. Okay, so let's look at an example. If we had 8x cubed minus 1. Well, the a value this time is 2x. Because 2 times 2 is 4, times 2 again is 8. X times x times x is x cubed. The b value is 1, because 1 times 1 is 1, times 1 again is still 1. Don't worry about the minus sign, we'll take care of that in the pattern. Alright, so it'll factor into a binomial times a trinomial. We fill in the a value, same sign as the original b value. Square the a value, so 2x times 2x gives us 4x squared. Do the opposite sign of the original, so because it was a minus to start out with, now we have a plus. Find the product of a and b, always positive, b squared. So there's your factorization, and again, if you multiplied that out, you would see that all of the inside terms would cancel out, and you'd be left with x cubed minus 1, 8x cubed minus 1, what you originally started with. We have an acronym to help you remember the signs when you're factoring the sum or difference of two cubes. The acronym is SOAP. The S stands for same sign, because the first sign in your factorization will always be the same as the original polynomial given to you. So if you started out with the sum of cubes, the first sign will be a plus. If you start out with the difference of cubes, the first sign will be a minus. The next letter, O, stands for opposite sign. And that's because the second sign in your factorization is always the opposite of whatever you started with. So if you start with the sum of cubes, your second sign will be a minus. If you start with difference of cubes, the second sign will be a plus. The final two letters in SOAP stand for always positive. And that is because the final sign in the factorization is always a plus sign. Doesn't matter if you have the sum of cubes or difference of cubes, this last sign is always plus. Let's take a look at some examples of factoring so we can apply this. Okay, so it says to factor the following completely. Remember that step 1 of factoring is always to check for a greatest common factor. So in this first problem, I immediately recognize that I have x as a common factor in every term. So I'm going to begin by factoring out that x and making x times x squared plus 2x minus 15. Now I have a trinomial, so I'm going to attempt to factor that with reverse FOIL. So I know my first terms have to multiply to x squared, so it's got to be x times x. My last terms have to multiply to negative 15, but add to positive 2 in the middle, so I need positive 5, negative 3. And there we are, completely factored. Number 2, this time I see, they're both even, so they're divisible by 2, and they're both divisible by y cubed. So I start by factoring out 2, y cubed. I'll be left with y squared, because 2 times 1 is 2, y cubed times y squared. Remember, we add exponents when you multiply the same base, so 3 plus 2 gives you 5, minus 9, because 2 times 9 is 18. And then the y cubed is all we need there. Alright, so now I have difference of squares, y squared minus 9. So I keep my GCF out front, and I'll factor into y plus 3 times y minus 3. On the third one, I see they're all divisible by 4 and a z squared. So I factor that out. I'll be left with z squared minus 4z plus 4. So that's a perfect square trinomial. It can factor into z minus 2. Z minus 2. So my complete factorization is 4z squared times z minus 2. Number 4 is our first sum of cubes practice problem. So I'm going to identify that a is x, b is 4. And so if you don't know your perfect cubes, you'll need to work on those. Create yourself a little note card cheat sheet, or just something where you can reference them and still you really know them by heart. So just go through and figure out, okay, what's 2 cubed, 3 cubed, 4 cubed, 5 cubed, and so on, and then just start to recognize and identify them. I knew 64 was 4 because 4 times 4 is 16, 16 times 4 is 64. It's even, it's not too large, but it is too big for 2 because 2 cubed was 8. So my next thing to try was 4, and that's what it is. Alright, so it factors into a binomial times a trinomial. We fill in a, same sign as the original, b, square a, opposite sign, product of ab, always positive, b squared. Although it may be enticing to attempt to factor this if you've correctly factored, so if you've taken out your greatest common factor first and then you've applied sum or difference of cubes, this should not be factorable. Once you've applied the pattern, you should be done factoring. Okay, number 5. Well, they're both even. You can think about 4, but it doesn't go in evenly to the second one. So it's just going to be 2z squared that we factor out. And we'll be left with 8z cubed minus 125. So I have difference of cubes. So I'm going to identify that a equals 2z and b equals 5. So I keep my GCF. It's going to factor into a binomial times a trinomial. So a, same sign as the original, b, square a, opposite sign of the original, product of ab, always positive, b squared. So there's my complete factorization. For number 6, why don't you pause the video, try it on your own, and come back and see how you did. Okay, if you were successful at factoring number 6, you should have identified that it was difference of cubes. A is 3x, b is 5, So it'll factor into a binomial times a trinomial, A, same sign as the original, B, square A, opposite sign as the original, find the product of A and B, always positive, B squared. And remember, that's just a pattern that you have to practice and memorize and be able to apply. There aren't any other tricks to it. Practice and memorization. Alright, number 7. Well, this time it's a difference, but it's not a cube. It's a fourth power, so that tells me it's probably going to follow the difference of squares pattern. Unfortunately, I don't have a GCF other than 1. So I'm going to jump in and try difference of squares. So I'll take their square roots and make it 4x squared plus 9, 4x squared minus 9, and check and see if it works. Well, I'd get 16x to the 4th minus 36x squared plus 36x squared, so outsides and insides would cancel, and I'd have my negative 81. But I notice that this again is difference of two perfect squares, so I gotta keep going. I'll keep my first factor. Second one I'll factor via difference of squares again. So it'll be 2x plus 3, 2x minus 3. Okay, number 8, we're back to a trinomial. Definitely a GCF here. Everything's divisible by 2 and a p squared. So we'll factor that out first. We're left with p to the 6 plus 5p cubed plus 6. So don't be alarmed by these higher exponents. That's our goal now, is to move beyond the quadratics to higher degree polynomials. We still use the same basic factoring strategies. So we'll keep our GCF and we'll attempt to factor this via reverse FOIL. I know that my first terms have to multiply to p to the 6th, and in the middle they have to add to p cubed, so that's a pretty good clue that I want p cubed and p cubed, and when I multiply p cubed times p cubed, you add the exponents. 3 plus 3 gives you the 6. Now I'm keeping in mind that I have to multiply to 6, but add to 5, so I want plus 3 plus 2, so that I'd have 2p cubed plus 3p cubed will give me 5p cubed in the middle. 3 times 2 would give me the 6. So there's the complete factorization. Okay, so try the beginning practice problems from pages 114 to 115, and then we'll come back and look at another factoring strategy and just continue to expand our factoring capabilities.